Hello. Hello, hello, hello. Hi, Quincy. Hi, Bobcat. Hannah, Andrew, Emily. I'm so happy to hear from all of you. I had just awful issues this morning when I was trying to stream for biochemistry, and I think that my immediate area might be overloading the internet, I guess, because the bit rate isn't high enough when I'm trying to stream, and I don't have that problem with you guys. I don't have that problem with you guys in the afternoon, so I think I'm going to have to move the time my other class is being offered, which is kind of weird, but I mean, this whole situation's kind of weird. I'm having Fancy Hat Friday. Feel free to join me and put on a fancy hat if you want. I know I can't see you, but I have lots of fancy hats, and it seems like Friday's a good time to wear a fancy hat. I don't know. So, all that said, I guess we can go ahead and get started. Make sure my phone's turned off. I got my model kits at the ready. Same molecules we've been working with. Pull up all my relevant screens. And minimize my less relevant screens. All right. So if I cut out or if I am not visible, please let me know ASAP. The chat box gets through much faster. It's basically instantaneous, whereas the video feed has, I don't know, maybe like a 20-30 second delay on it. So yeah, if for some reason I start buffering a lot or something like that, let me know. We're trying to work on this. My husband's been working on it for 2 hours. He's better with IT stuff than I am. I'm okay getting stuff set up, but I'm not okay fixing problems most of the time. So anyway, I'm happy to hear from all of you, and I hope everybody's doing okay. Is everybody still healthy? Anyone get the funk? Or are you just sick of being at home? I hope everybody's still healthy. Okay. Let me cut over to my painting window. Oh, Vinny, no. Someone you work with was exposed, so are they, hopefully they are at home? After passing out at home. Although, let's be honest, I think that the situation and everything that we hear on TV and everything is so stressful that it could very well make somebody pass out and, hyperventilate or something like that just from the stress of getting this condition. I have a couple of, this makes me sound like such a dork. I have a couple of internet friends who've come down with it. One is an infectious disease specialist at a hospital, and she's gotten it. So let's just hope everybody's doing okay. Our numbers in Clarksville are still low, but I know some of you travel from quite a ways away. Jocelyn, do you travel from Nashville? I feel like that's what I'm thinking, but anyway. All right, so let's go ahead and get started. I won't keep delaying our class, although, oh, there it is. I don't know where I put my pen. All right. So in class on Wednesday, I guess the phrasing of how I do things doesn't change. You know, I'm still used to just saying things certain ways, and that's how we do it. Oh, Pleasant View. Okay. All right. So more stereochemistry. I would like to start off with asking if we have any questions left over from Wednesday's class. So I know that, you know, some of you aren't able to watch this as it's happening, or maybe some of you are able and you just don't want to, which is fine too. I mean, we're making the best of what we can do, right? Making the best out of a bad situation. So, if you have any questions, or if you're like, hey, I would like another example of blank, I have dedicated a couple minutes today to answering any of those questions. Also, I don't know if you noticed, Dr. Hyatt sent out an email yesterday, and I don't know if you know Dr. Hyatt. She actually teaches an online class on the regular, actually, 2 of them. And she said that online students oftentimes like a checklist. And so if you can make them a checklist of things that they should be doing, that can kind of help keep them on track. So I made a checklist and I put it on D2L for you. So if you look at it and you're like, I was going to do all this anyway, ignore the checklist. I don't know. She just suggested it, and I thought it might not be a bad idea. I did put down that we're changing the number of chapters that we're covering for exam 3, because we did lose a week. So we're going to do 3 and 4, and then, I'm sorry, 5 and 6. And then for the last exam, we'll do 7 and 8, or as much of 8 as we can get through. And we'll just call it that for a semester. And Dr. Matthews will know that for summer, if you take him in summer. And if you, okay, I have to know who Barracuda Death Wish is. That's fun. Yeah, I'll do another mirror image example. And then also when I teach in the fall, I'll just start off with wherever we left off this semester, so it won't be a huge issue. Okay. All right, so Barracuda Death Wish. Yes, I will do another example for you. All right. Okay, so let me, oh, my pad turned off because I was, there we go. All right. Oh, also something really weird that happened in my class this morning is my, thanks, Katie. Wait, who's, oh, Catherine. I'm sorry, I never think of you as Katie. You would like this look because you also dress like an elderly woman like I do, so I wouldn't have you any other way. All right, so here we go. Let's do a more complicated example than the ones that we've been doing, because usually if you can get the harder ones, then the easier ones that you'll do are going to be a little bit easier to see, okay? So I'll just make a molecule. Got my wedge line. Got my dash line. Librarian look all the way. You definitely look like you could be a librarian. And I mean that in the most genuinely loving way possible. I love the way librarians look. All right. So here we go. Here is a La molecule. You can tell it's Friday, I'm getting a little quirky. It has been, I looked, 20 days since I've last seen you, and I can kind of start to tell because I'm like, I miss my people. All right. So I have my dotted line down the middle that is indicating I'm getting ready to draw a mirror image. That's kind of like a pretty consistent standard for how to kind of indicate that. So we basically just need to make it look like it's looking at itself in the mirror. And I think that probably the best place to get started with this would just be drawing. I think it's easiest to draw the straight lines first, not without these, because I can just kind of view that as its own component. Some of you might find that you like to view it or do it another way, but this is kind of how I do it. So if you look and just kind of ignore this OH and H, the blue and the yellow are essentially mirror images of each other. And then my OH, instead of coming out to the right at the bottom, it'll still be on the bottom, but it'll be coming out to the left. And then my hydrogen right there. Okay. So those would be mirror images of each other. If we wanted to go through, and while we have it up, we might as well come up with the stereochemistry, right? So here's the chiral carbon that's in question, which is the one that we drew in perspective, so hopefully that made sense. It would be easy to see that oxygen would have the highest atomic weight and hydrogen would have the lowest atomic weight. So those would be the two easiest to kind of determine. This carbon here is attached to two hydrogens and another carbon, whereas this is a carbon attached to no hydrogens, and you would basically look at it as being attached to 3 carbons, even though it's really just attached to 2, but because of the double bond, that's how the Kahn-Ingold-Prelog rules work. So that would mean the benzene ring would be number 2, and then this ethyl group would be number 3. Okay? So I'll give you a second to think back and how we determine whether we're looking at an R or an S isomer from this. Say, oh, I connect numbers 1 to 2 and 2 to 3, and that's going in a clockwise manner, so that is R. So if you were sitting at home and thinking, or wherever it is that you're sitting, yes, I think that's R stereochemistry. You're absolutely correct. Whereas the one in yellow would have to be S because it's the mirror image. Right? So you'll notice I didn't even work it out. It's the mirror image, so it's the only option, right? But if you wanted to, right, the designations didn't change. That's still number 2, that's still number 1, that's still number 3. So 1 to 2 to 3 would be counterclockwise, which would be S, sinister, for left-handed rotation. Okay? So Barracuda Death Wish, let me know if that kind of got you where you needed to be and answered any of your questions. I will go ahead and pick, I'll scroll down a little bit to give me some more room and say, here's an alternate way. All right. So an alternate way, let's start with the S. I'll just keep it that way. An alternate way to go about doing the mirror image would be to swap 2 groups. Okay, so I'll just keep this guy up here because I think it kind of makes sense that way. And then I like how Barracuda Deathwish isn't telling us who they are. Is the thing going behind always number 4? So Harlequin, to determine whether or not you're looking at an R or an S, number 4 must be pointing behind. Sometimes you can find a structure where number 4 is not pointing behind, and you need to basically rotate the image in your head or using a model kit. Rotate it so that number 4 is pointing behind and redraw it so you can come up with that. Another way you can do it is what I'm actually kind of doing here, where I said you can flip 2 groups and get the other isomer. Okay, so I went ahead and took this structure here and then flipped the OH and the and the hydrogen. So that would mean this would have to be R, all right? So what you can do, if you don't want to flip the image in your head, you can you can swap 2 groups. So number 4 is pointing behind, and you have to realize that when you swapped them, you swapped the stereochemistry. So if I had been given this picture before, and I thought, okay, I need to swap 2 groups, so I'll swap the OH and the H to make sure my hydrogen's behind, and that'll give me the opposite isomer of what I started with. So that is a way you can do it. I kind of feel like that can be confusing for some people, but drawing it out can also be confusing for people and trying to rotate it in their brain to do that. I did do a couple examples in class on, I think it was on Wednesday, it might have been on Monday, where we practiced just kind of what it looks like if I have it here, what happens if I rotate it, what happens if I rotate it, you know, and you can rotate something along all of these different axes, all of the sigma bonds essentially. So that's what I wanted to communicate with y'all. So hopefully that helps. Okay. So getting into our next topic is it's actually not different than what we've been talking about. It's just more of like a continuation. So all of chapter 5 is just looking at these type of perspective drawings and determining their stereochemistry based off these perspective drawings. So let me trying to come up with the best way to go about doing this. It doesn't want me to connect my dots. This is how we do chemistry now. Well, all right. I know. I'm sure that every single time I teach this, by the time I get to this point, everybody's like, why does she just keep drawing the same thing over and over and over again? Well, that's because I know how neurons are made. And I understand that the more you see something and the more you write it down, that actually makes you remember it better. So, what app am I using to draw these? This is actually, believe it or not, Microsoft Paint. I find that is the fastest and easiest way to go about doing stuff. It's a very no-fuss program. And so it's just what I've always used for this. Do you hate it or do you like it? I'm one of those people that got really sad when I was told that they were going to get rid of Microsoft Paint. I was like, no, and then they didn't get rid of it, so it's okay. It might just be because I'm old, I don't know. Maybe I like it because I'm old. Yeah, so in ChemSketch, I can't change the colors as easy to color code things. It takes more time. And I can't draw arrows as quickly. And also, it would be harder for you guys to keep up with how I'm drawing stuff because I can draw certain structures much, much faster in there. So, yeah. All right. So I'll go ahead and let you put in your examples for constitutional isomers and conformational isomers. For my enantiomers, I have my RS versions, or if I'm in a biochemistry class, I'll see those as the LD version. Or if I'm looking at really old literature, you might see LD, levorotatory, dextrorotatory, that kind of thing. And the way that we're seeing those exclusively is through, perspective drawings. We can't do designation of these type of enantiomers if we don't have the perspective drawings. So remember that in your head. If you don't show perspective, you didn't show perspective. You didn't show stereochemistry. With diastereomers, we learned about cis and trans so far. But I also need to talk about something that would look like this. ... Okay. So if you remember, and I'm assuming you do because you got nice sharp brains, you got young people brains. Makes it sound like you're zombies. You've been eating young people. Okay. So, well, let me actually just write down all of these. If you're thinking about constitutional isomers, you're thinking of molecules that have different connectivity. And so they're going to have different chemical and physical properties. Many of them could have different functional groups completely, right? So like 1-propanol and 2-propanol would have the same functional groups and would be able to react similarly. So their physical or their chemical properties would be very similar. But then you could also have an ether or something like that, and that would be very, very different. Then we've got the conformational. And those are different, basically different energy states based off rotation or flipping of the molecule. And so you actually can't separate conformational isomers. That's why some people don't really consider those isomers and they just call them conformational changes. But I was just kind of keeping it consistent with how your textbook does it. And then I've got the stereoisomers. Oh goodness, what did I have happen? Oh no. And stereoisomers are going to be different in how they rotate or how they fill up space, basically, which is kind of a weird way of thinking about it. But so up until this point, I've been telling you that enantiomers are non-superimposable mirror images. And as far as these go, they only rotate plane polarized light in opposite directions. And if they're in a biochemical system, they might be used or not used. Okay, but I'm not going to get into that in organic chemistry. You'll learn more about that in biochemistry. And so up until this point, I've talked about diastereomers in terms of just cis and trans. And so I haven't really given a whole lot of definition as to what the definition of a diastereomer is. I've only talked about it in terms of whether or not it was cis or trans. And I said, I'll tell you about the definition in a little bit when we've learned some other stuff. So I like to cover diastereomers definition after I talk about enantiomers for the simple fact that it's going to make more sense now. So non-superimposable non-mirror images. These can have different physical, well, can have different physical properties, really. We're not really looking at these in terms of having different see if I can do a thing. Give me just a second. Got cut off. I'm sorry. Okay. I think you know what it was saying though. Non-superimposable, non-mirror images. Okay. So I need to talk about that with you. And so what we're really going to be talking about with these diastereomers is you could be looking at cis-trans, or you could be looking at something with multiple chiral carbons. Okay. And so this is where we put our star for today. Okay. So that's our goal. Okay. So getting into diastereomers that are not cis-trans versions, I want you to think about molecules that have multiple chiral carbons. Okay. So there's absolutely nothing to state that you can have a molecule that can only have one chiral carbon at a time, right? Lots of sugars have lots of chiral carbons. And actually, one of the things we did early on in the semester, or early on in our discussion of chirality, is started to look at molecules and determine which of these were chiral and which ones were not. And so if we looked at this molecule and I said, you know, use a little asterisk, that little guy, to indicate whether or not you had a chiral carbon or not, you would go through and you would say, okay, that's one, that's one. This is not one because these are both CH3 groups right there. So those would be two of the same thing attached, right? And to be chiral, we have to have 4 different things attached. So that's our standard. So let's do this example of this molecule here. And let's think about what type of stereochemistry it could have, right? So I'll call this one, let's see, if we were to name this, we would number it thusly. So 2, 3, okay. And so I'll call this one carbon number 2, and this one's carbon number 3, because that's what we would be looking at, would be 2 and 3, okay? So options for stereochemistry is you could have 2R, 3R. Check. You could have 2S, 3S. Well, if you notice, 2RS, RS, those would actually be enantiomers, okay? Because those would be non-superimposable mirror images. Okay. Then I have an option where I have 2R, 3S, or 2S, 3R. These would also be enantiomers. And they would be enantiomers because they are, again, non-superimposable mirror images of each other, right? So if you have 100 different chiral carbons on a molecule and all of them have R stereochemistry. If you have the same molecule where all of them are S stereochemistry, you have the enantiomer. Okay, so the number of chiral carbons doesn't matter. You just have to make sure that for an enantiomer, the stereochemistry is all completely flipped. Okay, whether it's 1 chiral carbon or 12. All right. But I told you that we're going to be talking about diastereomers, so I'm going to bring back my green pen here. So if we were looking at diastereomers, that would be if we were comparing something like 2R and 3R to 2R, 3S. That would be a pair of diastereomers because those would be non-superimposable, non-mirror images. Okay, and so similarly, I could also have 2S, 3S, and 2R, 3S. That would be another diastereomer pair. You could have 2R, 3R, 2R, 3S. Oh, wait, I already said that one. Let's do it this way. So 2S, 3R. And then I'm kind of running out of room. I didn't plan that well how I drew that. So basically, if you had this molecule, you would have a total of 1, 2, 3, 4, 5, 6 different stereochemical configurations. I'm sorry, you would have 4 total different stereochemical configurations. 2 sets of those would be enantiomers. And then if you basically mixed and matched the others, you would have diastereomers. Okay? There is a reason that back in the second exam, I want you to remember about the cis-trans isomers. And at the time I said, your book will have you try and name these as a cis and trans as part of the name. And I said, I'm not going to have you do that because of reasons I'll tell you later. Now is the later. So I want you to look carefully at this chlorocyclohexanol that I'm drawing on my fake whiteboard. It's more like a blackboard with chalk, the way I did it, the way I set it up. Okay, so now I want to say, pick out the chiral carbons. And you're like, oh, we haven't really done that a lot with rings, right? But okay, there is not a plane of symmetry down this molecule in really any way I can draw it. There's no symmetry here. This one is chiral because it has 4 different groups attached to it. This one is chiral because it has 4 different groups attached to it. So previously, based off what we learned in class where we have one pointing up and one pointing down, we would say these are trans, right? And then I said, if you look at these molecules, you would actually have 2 trans options, one where it's like this and one where it's like that. That's because these are actually better viewed in terms of diastereomers. Or in terms of RS configurations. So remember, cis-trans tells you kind of the relative orientation. It tells you if they're doing this or this. It doesn't tell you which one you're looking at. But if you use R and S designation for these, you know exactly which one you're looking at. And so that makes these, it makes using R and S much more useful. And that's why I don't have you guys use cis and trans in your nomenclature. Like, it's important to know what the definition of cis and trans are. And it's important to know that you could have two trans forms or two cis forms. But if you were to buy those chemicals, you wouldn't know which one you were buying if that was the naming that they used. And so it's not all that useful when it comes down to it. Okay. So better viewed in terms of RS configurations. So let's come up with the actual stereochemistry of this molecule. I'm going to, oh, what did I do? I'm going to redraw it. And this way, if I redraw it, hopefully we'll see it in a way that might make it easier to figure out. I don't know. So the easy one is the one on top with the OH on it. And that's because the number 4 group is pointing behind the hydrogen. Okay? So that would be number 4. The oxygen would be number 1. And then I'd have to think, this is a carbon with 2 hydrogens on it and a carbon. This is a carbon with a hydrogen, a chlorine, and another carbon. So we can't use the carbon or the hydrogen to determine that, but we can use the chlorine. So the chlorine would have higher priority. Okay. So this would be number 2, and then this would be number 3. So if I hooked up my 1, 2, and my 3, that would be our stereochemistry at carbon number 1. Okay. Now, this is where I was saying in this example, it can be kind of hard to flip this molecule in your head because it's a ring, first off. And second off, we have 2 stereocenters. So if we determine this one is R, and then I flip the molecule like upside down or something to reorient this, it could be confusing for some people. So what I would do is kind of flip these 2 groups and just say, I understand that when I flip 2 groups, I'm actually coming up with the opposite stereochemistry. So chlorine would be number 1, the oxygen, or the carbon with the oxygen on it would be number 2, the CH3 or the CH2 group would be over there, okay? And so in this way, I would end up with 1, 2, 3. So this would be S stereochemistry. If that's S stereochemistry, though, it means up here I had to start off with R, or otherwise, like I flipped 2 groups to get the S. So I have to understand that I actually have the R. Okay, so I have 1R, 2R, and I could say, what would be the enantiomer of this? Well, you could look at that and say it would be 1S, 2S, okay? Or you could actually draw out the molecule. That would also be useful. And I would have my OH pointing out here. There we go. So for that one, I just did the mirror image, right? I used my little dotted line to indicate my mirror plane, and I came up with my structures there. So that would be a way to come up with an enantiomer. And if you wanted to do the diastereomers, you kind of just could pick and choose, right? And so what I mean by that is, let's see here. Shoot. Okay. So what I mean by that is enantiomers. If I wanted to draw a diastereomer for this molecule right here, I have two options. I could do the 1R2S or the 1S2R. Both of those would be enantiomers. What I need to do is pick which one I want. Doesn't matter. I'll keep my R how it is just because I can. And then for my bottom chiral carbon, right, I know that if I want the opposite stereochemistry, I just have to flip two groups. So, okay, instead of having my H pointing out and my chlorine pointing behind, I'll have my H pointing out and my chlorine pointing in the front. And so I know that that's S stereochemistry. So now if I'm looking between these two molecules, these are diastereomers. So I'm going to stop and pause there and see if this is making sense and see if you guys have any questions in particular. And I'll patiently wait and I'll drink some tea because it's Friday. Same as I do Monday, Tuesday, Wednesday, and Thursday. In fact, I'm going to pour more tea. In addition to fancy hats, I also have a lot of fancy teapots. If you've been in my office, you've seen a lot of them, but I have even more of them at home. Oh, good. I'm glad, Jocelyn. I was like, Jossie? No, Jocelyn? Just, you've always told me to call you Jocelyn, so that's what I'll go with. Yeah. And really, when you're talking about this, it's, Friday starts with an F. Well, I am drinking Formosa Oolong tea. That begins with an F. Does that count? Yeah, so, you know, when it comes down to how to draw these structures, it's always kind of a personal preference, really. You know, it's however you're finding that you like to do it the best, which is kind of up to you. And I know that that can be frustrating if I'm like, just do it how you want, you know? Because you're like, but what if I got it wrong, you know? So, oh, you guys are ridiculous. Okay. All right. So what I'm going to have you do then, in our next, how do I say this? In our next type of question, I'm going to do something, and I make my students do this every single semester, and I say, I'm going to give you two chiral carbons. Oh, I just realized, Quincy, I don't know why you actually said no. Were you saying no is like, because like that came through long after I said anything where no would be a normal response to me. So if I said, does this make sense? And you said no, please let me know if that's the case. Okay. So I need to actually put something on here. Let's do a hydrogen. Let's do a bromine. And hydrogen here. And an OH. Okay. So number one. name this molecule, including stereochemistry, meaning you're going to have to do the RS thing, okay? Number 2, draw its enantiomer. Number 3, draw the other 2 stereoisomers that are enantiomer, or that are diastereomers. And label their stereochemistry. Okay. So as far as naming goes, there's some information that would be useful to you. Actually, let's put another carbon there, so that way it's going to be easier to number it because they won't be symmetric. Okay. So easy way to think about this, right? If I were to just go through and name this molecule the old way that we've been doing, I'd say, okay, I have my longest chain of carbons right through there. It's my only chain of carbons, okay? So that's easy. And then if I number it so that the groups that are attached to it have the lowest possible number, I would have 1 here and 5 down there, which would mean I have some sort of pentane, right? So if I were to name this without any stereochemistry, I would have 3-bromo, pentan 2 all, okay? Because I have my hydroxyl group on carbon 2 and my bromine on carbon 3. All right. Now, this is where it can be confusing for people. I know I've said that a lot because this can be confusing for people. I'm going to go through and delete those numbers because we're going to have to put more numbers on to indicate those Kahn-Ingold-Prelog priority rules. And those are different than the numbering that we use just to do the naming of the molecule. So that's where people can start to get confused if they have all these different numbers posted around things. It's important that you're very clear in what those numbers mean. So what I'm trying to do here is fill in the following, basically. 2 stereoisomer, 3 stereoisomer. These always get put in parentheses at the beginning of a name. And now it probably makes sense why we like to number those specific groups. When even if you just have one chiral carbon, it's good to number it because if you have more than one, you need to know which one goes to which, right? So, okay, so name this molecule including the stereochemistry. So I basically need to fill in that there. And that shouldn't be too hard to do at this point for you. So let's look at carbon number 2. And I'll keep that one in yellow. So the OH group that's attached to this chiral carbon has the highest atomic weight as far as all the atoms attached to that attached to that carbon. Hydrogen has the least, so that makes it easy. And so then I have to compare a CH3 group to a CHBr group that has an extra couple carbons on it. So hopefully you look at that and say, yeah, the stuff down here would have higher Kahn-Ingold-Prelog priority over a methyl group. Okay. So if I were to connect my numbers 1 to 2 to 3, I'm going in this direction, which would be the R isomer. So carbon number 2 is 2R. Number 3, I'll do that in blue. The bromine is the clear winner here on highest atomic weight. The hydrogen is the lowest. And then the carbon with an OH on it, let me highlight that. the carbon with the OH on it would have priority over a carbon with another carbon attached to it. So I have 1, 2, the stuff up here would be 3, and then, oh, I see what I did. I'm sorry. I don't know if I said the right words or not, but if you guys were sitting there cringing, if you're like, why didn't she put a number 4 on the hydrogen? Because I'm special. Okay, there we go. All right. So now if I connect these numbers together, I'm still going in a clockwise manner. So this one is also the R isomer. So this would be 2R, 3R, 3-bromopentan 2-ol would be how, if you were to buy this chemical, that is what you would search for in the name on the chemical websites where you would buy this type of stuff, okay? So if I want to draw the enantiomer, which is what I asked you to do, which would be 2S3S, 3-bromopentan 2-ol. Easy way to go about doing that is to just draw the mirror image. Or you could go through and flip 2 groups, but you'd have to do it for both of the chiral carbons. Okay. So again, I like to start off with my straight lines. I find that easiest for me, but it kind of depends on what you find easiest. The main thing is you just have to work enough of these to get to the point that whatever you're doing is comfortable for you, and that you're doing something that gives you the right answers each time. Okay, so here is the enantiomer. I don't need to determine the stereochemistry on this because since I drew the mirror image, I know what it has to be. So this would have to be 2S, 3S, 2-bromo, pentan, 3-bromo, pentan, 2-ol. Oh, Barracuda. I'm glad that you have a emoji for elbow coughing. Okay. So this would be my enantiomer. Now, one other thing, I'll scroll back over there in a second. Draw the other 2 stereoisomers and label their stereochemistry. So I think that the easiest way to go about doing this actually, no, I don't want to do that. That's hard to see. Let me do this. Okay, yeah, just give me a second. God bless the eccentricity of the paint program. All right. So to do the 2 diastereomers of this molecule that I started with, right, this guy, I can go ahead and think about what those would be. I would have 2R3S as one option, and the other one would be 2S3R, which would be enantiomers of each other, but diastereomers of the molecule up here, which was the question, okay? So I'm going to do a little bit of scrolling here. So what I'm going to do first off is just start off with a skeleton type structure. I just kind of have to. And I need to basically, okay, so if I want one of these to be 2R, I can just draw it exactly the same way it is up here where we have the R stereochemistry. So I know that that's an R, and I can just do it that way, okay? The next one is that I need 3S. Well, okay, I've got 3S here, or I'm sorry, I've got 3R here. So to be 3S, I basically need to flip two groups. Well, I went ahead and drew the carbon skeleton first, which can make it kind of hard to go backwards, but I can flip two groups, and that would give me the 2R3S stereochemistry. Okay, and then to do the 2S3R, I would have two kind of options or choices. Number one would be I could just draw the mirror image of what I have here, okay? Or I could do kind of like what I did for this one to begin with. I know my bottom stereochemistry needs to be R, so it needs to look like what it looks like here. And I could flip two groups at the top to make that one the same stereochemistry. So I'll just do it with the mirror image, because that tends to be my preference. But I do like to kind of show you both ways. Okay, there we go. So those are the two other stereoisomers. So if we wanted to look at kind of the whole see if I can do this. I don't know what the resolution is going to look like though. Not terrible. I can see it well enough. So I hope that that kind of made sense on what I did there. What I'm going to need for you guys to do is to practice a few of these types of problems and let me know if you have any questions on those. I found a new, what was it called? A new system. For it's not Zoom. I don't know if any of your instructors are using Zoom. I I think it's okay, but all of you were like, nah, do YouTube. So I'm doing YouTube, and I hope that that's working out for you guys okay. I know it's a little different being removed from you guys, but really there's not that much difference in how I'm presenting the material. It's just my handwriting's even a little bit worse than it normally is. But I'm able to type faster. So it means that me drawing everything slower is still kind of turning out, I think, to be about the same amount of time as it would be in lecture. But anyway, I found a system for, let me find it. It is actually like a conferencing type of software where I can chat with you through your webcam. And it's supposedly easier than using Skype or using Zoom, because you don't have to have any extra programs downloaded. And so, I mean, like some of you might never use Skype or Zoom ever, so you might not have it on your phone or computer. This one goes straight through the internets, and all I have to do is give you a link, and you can just open the link and talk to me. So if that's a thing that you would need, I haven't worked with it yet. I just found it like at 2 in the morning. So if you want to ever use that, even if it's just to say, hi, I want to check in with you and, you know, I miss talking or whatever, because I know some of you guys like to come over to my office and talk. So I'll let you guys do whatever you want with that. But if you need it, just email me and I'll set up like the meeting, whatever, and send you the link. You can host up to 6 people at a time on it. So that makes it less useful for Zoom, like for a classroom setting than Zoom does, but I think it would work really well for office hours. So like I know like Lorena and Taylor, you guys tend to study together and work together a lot, but I'm guessing you're probably not together right now. Or Quincy and Joanna, or any of you guys that like to kind of study together in study groups, and you might be doing it remotely through phones or whatever. If you want to do like a group office hours or something, let me know. So that's that. Do some problems, work some problems in the book. Um, that'll give you the best options possible. It has a lot more comprehensive possible types of questions than what I have time to answer in any type of class setting. So just email me if you need anything. I'll see you guys on Monday. It won't be Fancy Hat Friday on Monday. So got that to look forward to. Maybe we'll do like pajamas on Monday or something. Got to keep it real. And yeah, just let me know if you have any questions. Like last time, I'll just stay on here for a couple minutes if you have questions. Or if you prefer to email me, that's okay too. I'm still getting the best reception in my husband's music room, so I guess. Oh gosh, this one's heavy. All right, so I guess we can just like play some bass while I wait. I have to pull up my chat box though. Dr. B's using Zoom. It cuts out a lot and lags. Yeah, so so is this when I do it in my morning class. So I really think that there's just a huge issue right now. I've been working, Brandon's been working, my husband, on trying to figure out why I've been having such trouble with my morning class, but I have no problems with you guys. Um, and I think it's just there's a lot of people watching Netflix right now. Honestly, I think that's what it is. I don't think that it's Zoom, and I don't think that it's YouTube in my case, because it works fine for you guys and Zoom works fine at other times. I really think there's just too much bleep going on right now with people online compared to normal. But you guys didn't know I play bass, did you? Or maybe you did, maybe I've told you. No, you do not, Andrew. That's not a thing I've ever asked a student ever to do on any exam. So that would be the type of thing that you would do in a physical chemistry lab. So you have to use the what? The optical rotation. Yeah, exactly. Um, you will not ever have to do that for an organic chemistry class, to my knowledge, ever, regardless of who you have. I don't think Dr. Matthews does it either, and he's more physicsy than I am. So, yeah, that would be a thing that you would do, though, if you were to take physical chemistry. I bet Dr. Chaparadza probably includes a lab where they have to do the optical rotation determination. We have the stuff to do it on campus, but yeah, that's not really within the scope of this class. It does sound mathy, doesn't it? Well, he said, do we have to calculate? Yeah, that would be kind of mathy, wouldn't it? The most that we do is adding up carbons and multiplying by 2, right? And there will be a couple other times where we have to do stuff like that specifically in organic too, but not the calculating optical rotation, like multiplying by 2. Okay. Well, if you guys don't have any questions right now, that's fine. Go ahead and just email me if you have any. Work some problems this weekend. It's important to just keep up with what we're doing and kind of acting like things are normal, even though they're not. But I miss your faces. I miss Hannah sitting in the front row being 8 feet tall, and I miss, Catherine sitting in the corner looking like a librarian, and Andrew's giant red beard, and Quincy in his button down shirts. Sad day. It's all right. Until we meet again, my friends, I will see you on Monday, I guess.